In the last section, we talked about electrical systems, rotational systems with gears, which completed our discussion of purely mechanical systems. Now, we move to systems that are hybrid of electrical and mechanical variables, the electromechanical systems. As the name suggests, electromechanical systems or device converts electrical energy into mechanical movement, and sometimes vice versa. Most of the common electromechanical components, such as electric motors and solenoids, are used in combinations with mechanical parts to provide actuations or movement. Our focus in this section will be modeling electromechanical systems for DC servo motors and derive the transfer functions, i.e., we want to look at the output and the input relationship of the systems. So our model, what we are going to look at, assuming that this is our system G of S, and our input into this motor is a voltage, let's say VA of T, and our output will be a rotation, because we are going to input an electrical voltage into the motor, and the motor is going to spin. When it spins, it's going to produce some displacement. So the output will be some rotation. This implies that we want our transfer function in this format: a rotation versus a voltage. So this particular motor, as we can see from here, it has a stationary permanent magnet. So this part here, this is your permanent magnet. And this permanent magnet, it produces the magnetic field, which allows the motor to keep spinning. Also, inside this motor, there is a rotating circuit called the armature, through which the current flows. This rotating circuit passes through this magnetic field at right angle and feels a force. And this force, you have F is equal to BL times AT, whereby this is your magnetic field strength and this is the length of the conductor. Applications of electromechanical system varies from industry to industry, such as in automotive industries, applications are such as braking systems, your electric windows, and windscreen wipers, etc., etc. It's also applied in robotics industry, such as your robotic arms and your crane systems. Also it's also used for tracking systems, such as your solar tracker and other tracking systems that use a servo motor. Also used in home appliances, such as your washing machines, extractors, and also with CNC machines. Another classical application of the electromechanical system is the disk drive. Here we have a DC motor schematic. Now, a DC motor is a combination of electrical systems and mechanical systems. In the following schematic, we have our electrical part, which is this side, and we have also the mechanical part, which is on this side. Now we are going to focus on the electrical part first. On the electrical part, we have our applied voltage, VA, and we have also a resistance here. Now, we say that the motor contains windings. These windings. Now, the windings has a certain cross-sectional area, meaning that if you pass a current through it, there is going to be a restriction, and that restriction is your resistance. So we model this resistance with this RA. We have also an inductance in the armature circuit. Also we have this VB. Now what happens is the VB is the motor. When the motor is being spun, it produces an electromotive force, also called the back EMF. And we have IAT. This is our current that is going through our circuit. And we know the faster the shaft spin, the bigger the back EMF. Also, the bigger the current, this current here, the more the torque. As you increase, this means this system, this motor, this is an armature controlled. This means what we have control over, we are controlling the current that is going through this circuit. And the more the current, the faster the motor is going to spin, hence the more the torque. So, since the current carrying armature is rotating in a magnetic field, its voltage is proportional to speed. So, meaning that your back EMF is equal to KB, which is your constant of proportionality, times theta dot m, which is your angular velocity. Now, the relationship between the armature current and the applied armature voltage and the back EMF is found by writing a loop equation, meaning that we need to write the loop equation first in order for us to see what is going on. And I'm going to write the loop equation below here. So what we have is, we have the supply voltage from the Kirchhoff's voltage law. Let me state the Kirchhoff voltage law first. Kirchhoff voltage law says that the sum of all the voltages should be equal to 0. And the sum of all the voltages that we have the supply voltage minus the voltage drop across the resistor, let's call that VR, minus the voltage drop across the inductor, let's call that VL, minus the voltage produced by the back EMF, let's call that VB, should be 0. Now, this implies that we have your supply voltage minus the voltage drop across the resistor, that is R times A, minus the voltage drop across the inductor, that's going to be L dia dt, and the voltage drop across, the voltage drop caused by the back EMF, this is just a voltage, which is equal to 0. So I can rewrite this as RA IA of t plus LA dia dt plus VB is equal to your supply voltage. So we can rewrite this equation and substituting our VB into the equation. So we are going to have RA IA of t plus LA dia dt KB theta dot m of t is equal to our applied voltage. From there we can take the Laplace transform. Taking the Laplace transform of this equation, we are going to have RA IA of S plus SLA IA of S plus SKB theta m of S is equal to VA of S. And we can factor the currents out so that we have SLA plus RA times your current plus SKB theta m of S is equal to VA of S. Let's call this equation 1. So we know that the torque developed by the motor is proportional to the armature current. So we can say that the torque is equal to KT times your current, whereby this is the torque developed by the motor, and this KT here, this is a constant of proportionality called the motor torque constant. So we can just say this is the motor torque constant and I is the current. So now it means that we have our current is equal to our torque over KT, because we say that the torque is proportional to the armature current. And we can take the Laplace transform of that, and we will have IFS is equal to our applied torque over KT. Let's call this equation 2. Now we can substitute equation 2 in equation 1. So let's say substitute 2 into 1. So we are going to have, so we can simplify this equation by S LA plus RA times the torque over KT plus SKB theta M is equal to the applied voltage. So we can call this equation 3. Next, we want to find the torque in terms of the rotation. If we are to separate the input and the output variable and obtain the transfer functions, because what we want, remember, is the rotation versus the input voltage. So in a nutshell, we want to relate the rotor torque to the angular displacement. To do this, we need to model the mechanical part of the system. And I'm just going to redraw the mechanical part below. So given the mechanical system, the applied torque is here, and once we apply the torque on this mechanical part, the system is going to rotate it's going to have a displacement theta m. And also, we are also going to have our inertial force on the opposite side. Let's call this J, and also some friction, we call that B. Note, torque is analogous to force. So we can say that the sum of all the torques, it's equal to 0. And now here we can see that we have a torque here, which is your applied torque, and we have also a inertial torque and also rotational damping torque. So the sum of all the torques is going to be your initial torque and your rotational damping torque, whereby we know that this is equal to J theta double dot plus B theta dot. We can take the Laplace transform of this. So from the Laplace transform, we are going to have tau of m in Laplace domain is equal to s squared J theta of s plus S B theta of S. I think I had a theta M, so let me just be consistent, then I'll put M there. So this implies that we have the torque is equal to J S squared plus S times B times the rotation. If we substitute this equation into equation 3, where the torque is, we have the torque here. We are going to have S times your inductance plus armature resistance times J S squared plus S times B theta M of S over KT plus S KB theta M of S is equal to our applied voltage. Now, assuming that the armature inductance is very small compared to the armature resistance, meaning that we can assume that this is 0, because if it's very, very small, then it's negligible. Then we can rewrite this equation and factoring out the RA over KT as RA KT times, which is equal to the applied voltage. So, and we can factor out as well the displacement, the theta m, out of the equation and rewrite it again. So if we have RA KT times JS squared plus BS plus SKB times theta ms is equal to your applied voltage. Also, remember what we are trying to achieve. What we want is our rotation over the applied voltage. And we can rewrite this equation and we can say that the rotation over the voltage, this is going to be this. Here you just do some manipulations, okay? Because if you take for example this equation first on this side, all right, then multiply both sides by VS, you'll end up having it on this side, okay? Just basic manipulations. So we are going to have 1 over RA times J over KT times S squared plus RAB over KT times S plus KB times S. Okay, so if we multiply through by KTRA, because we want to have this in standard form, so if I multiply both sides, top and bottom, by KTJRA, it will force this to be in the standard form. So we are going to rewrite this as on top we are going to have KTJRA over S squared plus SB times J plus KB KT over JRA times S. Just to clean up this equation again, what I can do is I can factor out again the S and the 1 over J. So to factor out S and 1 over J, we are going to have, I'm just rewriting this equation so that I have it in a very nice standard form, because as I said, if you are asked to find the pole location of a system, you need to be able to see which part is which. So we are going to have KT over J times RA over, we're pulling the S out, plus 1 over J times B plus KB KT over RA. Now this looks much better. Now what we can see here is we can rewrite this, assuming that this is overall, you can leave this equation in this format, okay? But if you want to simplify it and you want to see exactly what is going on, what you can say is, if we let this whole part to be alpha and we let this part to be K, then we can rewrite this equation as this is equal to K over S plus alpha. Now this format looks much better because it's easy to say is that, okay, our pole location is at minus alpha, and we have our gain K. Okay, and this means that looking at this system, we have two poles. You have a pole here which is at 0 at the center, and you have a pole here at minus alpha. And if you are asked to draw the pole location of this system, you are going to say, okay, we are going to have a pole at the origin and a pole at minus alpha, whatever that alpha is.